So, this is the last talk of this course, the 10 hours course of the part 2 of probability and stochastics for finance. It is a very, very broad subject matter. It needs a lot of understanding, lot of work. I myself need to study much more deeper, because mathematical finance is a very, very big area. What I am going to show you now is that how do you calculate this delta t, that you are at every time t, how do you know how much stock to buy, which was very simple in the case of the 2-period model. Now, so the title of this lecture is final lecture. This is a relaxed, my 10 hours schedule is over, this is just bonus. So, here the key to finding this is done by using something called a Martingale representation theorem. So, what is the Martingale representation theorem? So, Martingale representation theorem says, give me any martingale, right, which is adapted to a filtration associated with a Brownian motion. So, you will have the Brownian motion, you have the filtration associated with the Brownian motion, and also you have MT adapted to the filtration, FT, and is a martingale. So, how Martingale representation theorem says, how do I represent the martingale? So, it says that there would exist an adapted process, is adapted to the filtration, tau u. There exists an adapted process tau u, such that, so this is the delta, this is very important, this quantity, such that MT is equal to M0 plus 0 to T tau u dWu. So, this is called the Martingale representation process. Every what does it say? It says every martingale can be represented as an Ito integral, that is the whole thing. It is called the Martingale representation theorem. Every martingale can be represented as an Ito integral. Okay. Now, once this is done, it is easy to figure out how to do that. It does not matter if you have a martingale under the Brownian motion under P tilde, you will have the similar sort of representation theorem. So, I am not getting into the details of this. So, if I look at our process or our risk neutral valuation, so this is something we have already seen. This formula is now known to us. So, this is a martingale, this is known to us, because this was xt and this is capital XT, which is Vt. Okay. You can prove, in fact, sorry, in the risk neutral measure, you can prove this is a Martingale. When I do not want to prove it, it is obviously you can understand it is just the same thing that we have done earlier. Now, if this is a Martingale, then it must have a representation. So, there must be some gamma u So, I am doing the representation with respect to the risk neutral measure. D0 is 1, that is why just you have V0. Now, we have also seen that dtxt, we have also proved it earlier, was x0 plus 0 to t delta u sigma u su dwu. We have seen this, we have proved the Martingale, the fact that this is a Martingale by using the fact that this Ito integral is a Martingale. Now, sorry, this is x0. Now, what do we know? We know that Vt must be equal to xt and V0 is equal to x0, that is what we know. So, in order that these two are same, these two integrals must also coincide. This can be done if we choose delta t sigma t st is equal to tau u. So, if I choose this tau u or tau tilde u, does not matter. So, delta t, so there must be some process with respect to which this is the delta t. Okay, that is enough for our course. This was just an. So, we have done a large amount of work here. We started with the very basic notions of interest rates, then yield of curves, then optimization models in finance, then we went to portfolio optimization, for which we made a detailed study, then a brief outline of the capital asset pricing model, then we did the option pricing in the discrete time and option pricing in the continuous time. So, in this 10 hours time, a huge amount of material has been packed in. So, you need to also consult books, you need to consult the net, be careful when you take things from the net. I have also shown books, for example, this book which I want to show again and again, I have shown in the part 1, that these two books of stochastic calculus for finance by Shreve, volume 1 and volume 2. The fat one is volume 2, which is for continuous time, and volume 1 is for discrete time. They should be a must, if for anybody working in finance, anybody who likes finance, mathematical finance should have these two books. So, with this I hope that you have enjoyed the course. You can give the feedback, my TAs would come back if there are questions, about the teaching methodology. But I would again reiterate that please do not put in personal emails to me stating that, oh, you should have taught us Lebesgue integral, and some people might say, oh, you should have discussed Ito's formula before you did all these things. But again and again I am telling Ito's formula has already been done in detail in part 1, so cannot be done here now. This is the part 2 of a course, of which it is good if you have a look at the part 1. We are expecting a lot of things from the student, that in finance there is a lot of pressure on the quants, the guys who work in quantitative finance, is that they have to have a hold on lot of aspects of mathematics. It is not just they have to know some probability and then they can just go off, or some stochastic process. They have to have a hold on lot of aspects of mathematics, and this actually puts an immense pressure on them. So, here I am expecting that the students would have a lot of some basic knowledge of probability, some basic knowledge of stochastic process, they would know what a normal distribution is, etc., etc., etc. There are certain assumptions under which I am working. It is not a very basic or introductory course about Lebesgue integration. So, I had a student writing to me that, oh, you did not bother about teaching Lebesgue integration in details, but possibly they do not know that Lebesgue integration is a complete course. Mathematics is a deep thing. Mathematics is not about solving some complicated problems by algebraic manipulation, it is about deep ideas. So, this I also tell you that this is just the beginning of finance, you are in the complete market. Real market is incomplete. How would you handle things in the incomplete market is a very fundamental issue of research. Nowadays, there is new ideas called indifference pricings, etc., which has come into the market. There is a lot of things which had been studied in the theory of risk using convex analysis, for example. So, those a lot of things can be studied. So, the mathematical finance is indeed a very broad area, and it involves very good deep mathematics, but it is not always that the things that you do here is practically viable, because these things, these models are built under very ideal conditions. Just in physics you build models under ideal assumptions which may not exactly be replicated in nature. Here also things that we do here may not be exactly be replicated in the market, may not be exactly, the market may not be exactly as that. But these models helps us, just like in physics, to understand some aspects of how financial markets behave. So, financial markets also have this human aspect into it, which we are not going to it, called behavioral finance. But here it is mathematical models which actually help us to do some pricing, which helps us to gauge what should be my investment. So, here mathematics does play a very important role. So, I hope that a large part of you, large number of you who have enjoyed the course, and I am sorry if there is someone who has been left out from the whole discussion, not finding it comfortable. Our TAs, my TAs would be very happy to help them. So, thank you once again. I wish some of you who has done both the part of this course would actually become a quant and take up mathematical finance in the future. Thank you.